All right, so we we simplified square roots yesterday, right? Today we're just going to look at doing some arithmetic with square roots. Why don't you click them all closed, put everything away. So, it's adding, subtracting, multiplying, and dividing square roots. How do we deal with that? Well, it's adding and subtracting could not be easier. Very, very simple. When you're adding up radicals, you just add up like terms, right? Like radicals would be the same thing as like treating it like terms with variables. How do you know if you can combine terms if you have like radicals? Like radicals have to have two parts. They have to have the same index, meaning they have to be the same kind of root. They both have to be square roots, or they both have to be cube roots, right? And the other thing is they have to have the same radicand. You have to be taking roots of the same number. So here's an example where these are like radicals because they're both square roots of 5, right? So we can combine those just like we had 3x plus 6x would give us 9x. Here we get 9 times the square root of 5. Here's an example of unlike radicals that can't be combined. They can't be combined. Even though they have the same number inside, which looks good, notice that this one's a cube root and this one's a square root, so they're different. Can't combine them. Okay? Give me 1 to 5. Is that all? You guys have talked about this, I'm sure. Is that making sense? Okay. Let's just practice a little bit. So, top one. Everybody stare at that for a second. What am I going to get? No. No. If I add up, why radical 6? Okay, but if I had, so that would be like saying if I had x plus 7x, I'd get 7 times like 2x or something. What would you get if you added those up? You'd get 8x, wouldn't you? Okay, so we'll treat this the same. We treat like radicals just like variables. We're just counting up the numbers of those things, right? If I go back and I look at this statement here, what is this really saying? Anytime I have a number out in front of something, it's a coefficient. It's just telling me the number of those things. 3 of those guys plus 6 of those guys is 9 of those guys, right? The square roots of 5 don't change. We're just adding up the numbers of those. Same thing here. I've got 1 square root of 3 plus 7 more square roots of 3 is how many square roots of 3? 8. Yeah, exactly. Just like this would equal 8x, this equals 8 times the square root of 3. Okay, does that make sense? So you're not changing the radical when you're adding or subtracting. You're just combining like terms if you can. What am I going to get here? Next one. 6 radical 2. Yeah, I've got 10 of them minus 4 of them is 6 of them. And by them, I mean square roots of 2. Okay, next one. Ooh, see people shaking their heads. How come? Doesn't work. I can't combine them, can I? That's as far as I can go. Can't do. I have to leave it that way. Can't simplify. How about the bottom one? Give me thumbs on it. Are those like radicals? No, they're not. So I'm stuck. Can't simplify that one either, right? They're both square roots, but they're different numbers inside, so we can't combine them. All right. What about those? Can I do anything there? At first glance, it looks like you can't, right? Because I've got different kinds of radicals. They may have an idea, though. Any ideas? Anybody see anything I might be able to do to those square roots? Kind of deals with the stuff we talked about yesterday. Yeah, we could simplify those square roots, couldn't we? When we simplify square roots, what's our job again? Like, what are we trying to do? If I'm taking the square root of 20, what am I trying to accomplish by simplifying that square root? Kind of, right? The goal, remember, the goal is to get as much out of the radical as possible. Okay, we have a pretty big number inside the square root now. Can we simplify that so we can write it with a much smaller number inside? Okay, this is, how did we do this yesterday? What was our saying? We make a factor tree. Okay, so let's do that. Let's take the 20 and let's make a factor tree. What do we get? 4 and 5. That works. And then can I go, that's prime, right? Can I go further? 2 and 2. And you might have picked a different route in your factor tree. You end up at the same place. Now, what do we do with our factor tree? What's our little saying that couples go out, singles stay in? Okay, so what's going to go outside of the radical with the 20? The 2, yeah. Okay, so the square, this tells us square root of 20, the outside part is going to be 2, right? I only put 1 2 out there though, right? For each couple, they donate one outside number, okay? What's stuck inside? The 5, yeah. Okay, good. Now, how about the 45? Maybe we can do something with that. Yeah, that breaks up into 9 and 5. 5's prime. 9 breaks up into. Okay, so what's that tell us? The square root of 45 gives us what outside? 3. And what inside? Okay, well that's going to help, isn't it? Because now look, we can see that we're going to get the same kinds of square roots. So we should be able to combine these terms, right? Okay, let's see what we get here. So we can kind of, like we would, I'm just going to do this because this is a little different approach than what we're taking. Well, we could talk about it. The stuff we did yesterday would really take us from this step that takes us all the way down to there, doesn't it? Factor tree and couples go out, singles stay in takes us down to there. And then what do we have? So we combine outside numbers. We already had a 2 outside. So that stays there, right? And then we've got our 3 outside. So that gives us 2 times 3 is 6. Here I've got 2. So I get 2 radical 5 plus 6 radical 5 is what? Yeah, 8 times the square root of 5, isn't it? Yep, good. Okay, so I like couples go out, singles stay in because it works for arbitrarily big radicands. I mean, you could have really big numbers in there and this approach is still going to work. There is another way to look at this. And as you get better and better at simplifying square roots, you might start taking some shortcuts. Another way to do this is we could always try to find the biggest perfect square factor of the radicand. So we could look at 20 and we could ask ourselves, okay, if I look at my list of perfect squares, what's the biggest perfect square number that divides into 20? And what is it? 4, that's it, right? So then I would just split this into the square root of 4 times the square root of whatever else multiplies to 20, which is 5, right? How come I do that? Because the square root of a perfect square just gives me a whole number, right? So when you're dealing with small numbers like this, that's an okay way to do it. With big numbers, I would stick with couples go out, singles stay in. And you can always do the factor tree and couples go out, singles stay in if you want to. Same thing with 45. If we look at 45, is there a perfect square factor that divides into 45? And if so, what's the biggest one? What's the biggest perfect square factor of 45? If you want to organize your search on this, there's another little trick you can do. And I don't want to overdo this, but if the number inside the radical is not a perfect square itself, and 20 and 45, neither one of those is a perfect square, when you start your search for perfect square factors, they would have to be half of the number inside or smaller, right? So for 45, there'd be no reason to consider 36 because 36 isn't going to divide into 35, right? Only numbers that are half of the inside number or smaller could ever divide into it. So like if we were looking for 45, half of 45 is 22 and a half. So I would just immediately start my list at 16, right? Because 25 is too big and just work down from there and see if any of those divide in evenly. Does that make sense what I'm saying? It's kind of a strategy. Again, like as you do more and more of these, you can kind of practice that a little bit, and it'll just naturally come to you. But you can always go back and just rely on couples go out, singles stay in too. So what is the biggest perfect square factor of 45? 9. Yeah, right. So I would split the 45 into a square root of 9 because that's a perfect square, and then whatever's left, which is 5. And again, the reason I'm doing that is because the square root of 9 is 3. It gives me a whole number outside. You guys get that? Okay, let's try one more just for practice. Like, what if I gave you something like, let's see. How about this? What if we did square root of a pretty big one, 108? Is that right? Yeah. Can we do that one using our shortcut? So let me ask you this, is 108 a perfect square? Thumbs up or down? It's not, right? Okay, so then we would just start at half of 108 and work up and see if we can find something that divides into 108, a perfect square that divides into 108 evenly. What's half of 108? 54. So on our list, 54 would fall right there, wouldn't it? Between 49 and 64. So we would just start at 49 and work our way up, and let's just try them out. Does 49 divide into 108? Doesn't. Does 36? It does. 36 times what is 108? 3. Yeah, right. So we could break this up into square root of 36 times square root of 3. And what's that give us? What's that give us? 6. Yeah, exactly, right? That's why we found that perfect square, because it's giving us our outside number, which is 6 times square root of 3. Now, if we did couples go out, singles stay in, it's fine. Of course it's going to work. We'd get the same thing. We'd probably, like, remember, our goal is if we can get a perfect square factor, we will. Well, maybe we find that 36 right away. We get 36 and 3. And then what would we break 36 into? 6 and 6. So look, I immediately get a couple of 6s and a single 3. So I get to the same place, don't I? Right? Okay. All right. Again, I don't want to overdo that, but I just want to make you aware. I mean, you guys are a pretty sharp group. I think you might be able to just see that stuff quicker without having to maybe write down the whole factor tree. Okay. All right. Where were we here? Okay, good. Let's see. Right. Did that. Okay. Why don't you go try one of these? Go try one of those. Okay, so I think everybody was certainly on the right track here. Everybody got -6 radical 3. And I like the way you guys wrote it down better than this way. So just kind of ignore. In fact, for the notes, I'm just going to do this. We're just going to jump all the way down to there. Like that. I like that better. That's what you guys did. Okay, good. All right, what about multiplying? Okay, multiplying, no big deal, right? We multiply, square roots are just numbers. So we would do, like, everybody see that if I'm doing this first example, all I'm going to do here is distribute like normal, right? I've got something multiplied by a quantity, so I'm just going to distribute the square root like normal. Everybody see that? Okay, what is the square root of 5 times 6? Well, it's just 6 times the square root of 5. Nothing we can do there. How about the square root of 5 times 50? What am I going to do with that? Square root of 5 times 50. I could. Yeah, I could. There's a couple things I could do here. I could, if I wanted to, remember we have a property. If I have a square root of 5 times a square root of 50, I could combine those into one big square root, right? Thank you. Right, we know, remember this property? We know that the square root of A times the square root of B is equal to what? What is it again? Square root of A times B, yeah, right? We can go either way with that, right? So we could combine those if we wanted to into a square root of 250. Now, I don't think that Allie has an idea, like maybe we don't need to do that necessarily, right? You see something better, but let's just think of it that way for a second. I could combine all this stuff into a square root of 250. Now, if I made a factor tree with 250, what are some pretty obvious things that multiply to 250? 5 and 50, right? Because those are the things I multiplied to get 250. So why don't you just start on your factor tree right there? We don't even need to do the 250 part, do we? We already know that the first branch in our factor tree is just going to give us 5 and 50, right? Give me thumbs on that. Does that make sense? Okay, so then I just want to go from there. Okay, the 5 is prime. What can I do with the 50? Say it again. 5 and 10? Okay, I like that. How come 5 is such a good idea? Because I already have a 5. Exactly, yeah, right? So we could break this into 5 and 10, and look, I've got a couple of 5s, don't I? Okay. The 10, am I going to get another couple out of the 10? I am? What am I going to get out of the 10 that's a couple? I'm going to get a 2 and a 5, aren't I? I'm going to get a single 2 and a single 5. I could write them down, but I don't even really need to, right? Because if I take that step, I realize that I'm going to get my couple of 5s outside, right? Look at this. Here's my cup. Whoops. What did I just do? Yikes. There's my couple of 5s, gives me that 5. And then the rest of the stuff is just going to give me a 10 inside, a single 2 and a single 5. So don't even bother doing that. Don't even bother breaking that one down. We already know that that one's going to give us just singles, so put it inside. Make sense? Give me thumbs on that. Everybody see the logic on that? Okay. And I can't combine stuff from there, can I? Anybody agree? I mean, like those are not like terms. I've got a square root of 10 here and a square root of 5, so I'm stuck. That's my answer. Okay. Give me 1 to 5 in that whole process. Okay, good. How about over here, what would I do? Yeah, I'm just going to FOIL, right? Just distribute. So what's that give me if I distribute? Let's see, let's take this piece by piece. I'm going to distribute the square root of 11 to the square root of 3. What is square root of 11 times square root of 3? Square root of 33. Yeah. If I break up 33 using a factor tree, the only factors of 33 are 3 and 11. Agreed? Those are both prime. No couples, right? So everything stays inside. So there's my first step. Okay, what about the next one? Let's see. If I distribute the square root of 11 over to the 2, what's the square root of 11 times 2? 2 times the square root of 11, right? 11, there are no couples contained in 11. 11 is prime. So my next term is just going to be plus 2 times the square root of 11. Okay, give me thumbs. How we doing? Okay. Then let's do the next one. Now I've got to distribute my negative square root of 7. Negative square root of 7 times square root of 3. What's that going to be? Negative times positive is negative. Okay. And square root of 7 times square root of 3. What's that going to be? Say it again. Square root of 21. Are there any couples in 21 if I make a factor tree? No. 21 just breaks into 7 and 3, right? So I'm stuck with square root of 21, right? And then finally, last one, negative square root of 7 times 2. What's that? Negative 2. Square root of 7, exactly, yeah, right? Because the 2 is outside already, so we just get that. Are there any like terms to combine? Thumbs up or down? You see any like terms? Where? Okay. Okay, how come no? You changed your mind. Okay, you saw the 2's, but what's the important part? The square roots. Yeah, notice all those square roots are different. None of them are like radicals, so I can't combine anything here. Okay, that's my answer. Okay. Yes. Does that make sense? You were thinking maybe you could break one of these down? Okay, good. Yeah, because it breaks into 3 and 11, no couples. Good, good. Okay. Okay, last part here. What if we have a fraction that involves square roots? That's fine, except the thing is we don't want radicals in the denominator, okay, in math. So we need to get rid of those. We need to rewrite the expression with no radicals in the denominator. We call that rationalizing the denominator. Can anybody think of a trick we could do? And what do we normally do in situations like this, right? We multiply the top and the bottom of the fraction by the same thing. So I'm really just multiplying by 1. I'm not changing the value. What could I multiply the top and the bottom by here so that I end up with no square root on the bottom? What could I multiply the square root of 2 by to get no square root as a result? What do you mean by that? I see this. You mean 2, or do you mean 2 times the square root of 2 is just 2 times the square root of 2? But what were you thinking? I think you had a good idea. I'm sure you did. Yeah, square root of 2. Exactly, right? Yeah, look what happens if we multiply the top and the bottom by the square root of 2, then on the bottom, everybody, what is the square root of 2 times the square root of 2? No, 2, exactly, right? Because that's like saying now I've got a couple of 2's. What is the square root of 2 times the square root of 2? There's 2 ways to think about this. The square root of 2 times the square root of 2 is the square root of what number? 4. And what is the square root of number? Or square root of 4, sorry. 2, yeah. Okay. An even better way to think about it is this way. The square root of 2 times the square root of 2 is the square root of 2 squared. Anytime I multiply something by itself, it squares it. What does a square do to a square root? Cancels it out, exactly. So we just end up with 2, right? So there's our strategy. How do we remember this, that we have to rationalize denominators? Just remember the saying, no tenths in the basement. Can't have any square roots below the fraction bar, okay? And so when we multiply straight across, on the bottom, we're going to get 2. What are we going to get on the top? Square root of 3 times square root of 2 is what? Square root of 6. Okay, and that's fine. We can have square roots upstairs, or have tenths upstairs, right? Just no tenths in the basement, right? So, okay, make sense? Okay. Okay, what about this one then? Okay, I could just split it up. I could just split it up and go from there. That would work. If I do that, I'm getting pretty big square roots, square root of 48 and square root of 30. Does anybody see maybe a step we could do prior to that, before we split it, that might make things a little simpler? What's that mean? Okay, yeah, we could reduce the fraction. There you go, right? Because now all this stuff is inside the radical. So even PEMDAS tells us we're going to work inside parentheses. Well, everything is grouped inside the radical. So we'll always try to simplify inside first. What's the biggest number that divides into 48 and 30? 6 goes into both. There you go. 48 divided by 6 is what? 8. 30 divided by 6 is? Oh, beautiful. Okay, so look at that. That's a good idea. Reduce the fraction inside the radical first to make our lives easier. Okay, do you have to do it that way? No, it would work the other way, but it's a lot more work, right? Okay, so now what do? Split them, right? We split the radical. So we get square root of 8 on top, square root of 5 on the bottom. Good. Split the square root. Okay, are we done? What's the problem with that? No tens in the basement. Yeah, okay, we got to get rid of that. So how are we going to get rid of the square root of 5? Good. We multiply both the top and bottom by whatever the stranded square root is in the bottom, right? Okay. Oh, by the way, something else we want to do. Yeah, I should have mentioned this. We'd rather make everything as small as possible before we rationalize the denominator. So always simplify all the radicals first. We were looking at the bottom, which can't be simplified, but the top could, right? If I made a factor tree out of 8, 8 breaks up into 4 and 2, so I get 2, 2, and 2. Look, I get a couple of 2's and a single 2, right? So a 2 outside and a 2 inside. Okay, now, good. Now we're going to go ahead and rationalize the denominator. Okay, multiply top and bottom by the square root of 5. So what do I get on the bottom? 5. Good. What do I get on the top? Remember, I have to multiply things. When I multiply a bunch of stuff, I have to multiply in pairs. So I've really got 3 things being multiplied on the top. 2 times the square root of 2 times the square root of 5. Well, which of those 2 things do I probably want to multiply first? Square roots. What's the square root of 2 times the square root of 5? Yeah, and then I've just got a 2 outside, right? Everybody agree? So this stuff right here, we would just combine into a single radical. Okay? And then we'd look at the square root and ask ourselves, could we break it down further? But are there any couples contained in the factor tree for 10? No. So we're stuck, right? That's where we land on that one. Give me 1 to 5. Does that all make sense? Okay. All right, we're about done. I want you guys to maybe try one of those. So go to the board and give that a shot.